Have you ever actually stopped to wonder what's really going on behind the screens? Inside those power bricks or just running silently through the walls of your room right now? We literally live our entire lives completely surrounded by these invisible forces that power, well, everything. But for most of us, it just kind of feels like magic, right? You plug something into a wall and boom, it works. But what if we could actually visualize the hidden mechanics behind all that energy? What if we could actually see the traffic flowing right under our fingertips?
Well, welcome to our explainer. Today we're demystifying electrical circuits and taking a really calm, structured walk down what I like to call the invisible highway. Look, if you're a college student feeling totally overwhelmed by a wall of complex equations, or even if you're just a curious mind wanting to understand how the world works, just take a breath. We're going to step away from the heavy math for a bit and focus purely on the core concepts. The goal here is to build your intuition, step by step, so that you can actually visualize how electricity behaves in the real world. To build that intuition, we're going to follow a really straightforward roadmap today. First, we'll look at the spark of charge. Then, flow and force. Third, the actual circuit building blocks. Fourth, the anatomy of a network. And finally, we'll wrap up with the universal circuit laws. All right, let's jump into Section 1, the spark of charge, and understand those fundamental particles. Okay, before we can even talk about electricity, we absolutely have to have something called charge. Charge is the fundamental, absolute baseline property of particles. In our universe, protons carry a positive charge and electrons carry a negative charge. It's really this basic existence of positive and negative and their natural desire to interact with each other that creates every single thing we're about to talk about. And just for the record, we measure this property in a unit called coulombs.
Now, what's genuinely fascinating here is just how infinitesimally small a single charge actually is. Get this, the charge of one single electron is negative 1.6 times 10 to the power of negative 19 coulombs. That is a ridiculously tiny number. To put that into perspective, it means that when you flick on a simple desk lamp, you aren't just dealing with a few electrons. You are dealing with literal quintillions of these microscopic vehicles swarming down our invisible highway every single second. It's mind-boggling. Moving on to Section 2, flow and force. This is all about current, voltage, and power. So, when those massive, swarming crowds of electrons start moving together in a unified direction, we call that electric current. It's simply the rate of flow of electric charge over time, and we measure it in amps, or just amps. If we go back to our invisible highway analogy, the current is quite literally the traffic. Now, interestingly enough, individual electrons actually move surprisingly slowly, sometimes slower than a snail, but the chain reaction of them pushing each other happens at near the speed of light. Current is just a measure of how many of those cars, or how much charge, is passing a specific point on the road every single second. But here's the thing, traffic doesn't just move on its own, right? It needs a reason to go from point A to point B, and that brings us to electric potential, which is way better known as voltage. Voltage is the amount of work required to move a unit charge from one place to another. So the absolute crucial takeaway here is that voltage is the push. It's the pressure. If current is water flowing through a pipe, voltage is the heavy-duty water pump forcing it forward. Without voltage, our electrons are just sitting perfectly still in a permanent traffic jam. And when we combine those two, when we multiply that flow by that force, so current times voltage, we get power. Power is the actual rate at which real work is being done. It's the tangible, real-world result of all this invisible motion we've been talking about. This is the heat radiating off your electric stove, the bright light shining from your monitor, or the physical torque spinning a DC motor. It's that beautiful combination of pressure and flow translating into usable, everyday energy. Section 3, circuit building blocks. Let's look at active versus passive elements. When engineers build these invisible highways, they use physical components that cleanly fall into two main families, active and passive. Active elements are basically the suppliers. These are your batteries, your voltage sources, your current sources, the things pumping raw energy into the circuit. Passive elements, on the flip side, are the consumers and the stores. Resistors burn off energy as heat, while components like inductors and capacitors actually store energy temporarily, kind of like microscopic holding tanks using magnetic or electric fields. Now, engineers take this a step further and classify these passive elements based on how predictably they behave under pressure. For example, a linear element behaves perfectly consistently as the voltage and current change. A nonlinear element, like a diode, not so much. It changes its behavior on the fly. We also have unilateral elements that act like strict one-way streets, only letting traffic flow in a specific direction.
Meanwhile, bilateral elements, like a standard resistor, are totally fine letting current flow comfortably either way. Understanding these rules is exactly how engineers select the perfect part to control the traffic. All right, Section 4, Anatomy of a Network. Let's talk about nodes, branches, and loops. When you look at a circuit diagram for the first time, it can honestly look pretty intimidating. Just a bunch of squiggly lines and boxes. But here's the secret. Every single complex electronic device you own, from the smartwatch on your wrist to a satellite orbiting the Earth, can ultimately be broken down into a few simple connected shapes. If we just treat a circuit layout exactly like a city roadmap, it suddenly becomes incredibly easy to navigate. To confidently read that map, we just need a shared vocabulary. First up, a node. This is simply an intersection where two or more roads meet. Easy enough. Next, a branch. Think of a branch as a direct path or a single street joining two intersections together. This is exactly where our active and passive elements live and do their jobs. And finally, a loop, which is just a closed path. If you can start at one node, drive around the circuit, and arrive back at the exact same starting point without retracing your steps, congratulations, you've just completed a loop. Finally, Section 5, Universal Circuit Laws. These are the absolute rules governing the flow. First up is the absolute golden rule of electronics, Ohm's law. It states that the current passing through a conductor is directly proportional to the voltage across it. V equals I times R. This elegant, ridiculously simple equation eternally links our three main players. It tells us that if you increase the push, the voltage, you naturally get more traffic, the current. But if you increase the resistance, that traffic is going to slow down. It is the ultimate perfect balancing act of our invisible highway. Then we have the laws mapped out by a physicist named Gustav Kirchhoff. Kirchhoff's current law, or KCL, sounds super formal, but the underlying logic is beautifully simple. It just states that the sum of currents meeting at a node is zero. Put into plain English, whatever traffic drives into an intersection absolutely must drive out. Cars don't just magically disappear into thin air, and neither do electrons. When you visualize this, it proves that exact point perfectly. If you track the flow heading toward a center intersection, say two streams of current are driving in, then because nothing is lost or magically created out of the void, the exact same amount of current leaving that intersection through other paths must absolutely equal what came in. It's a flawless conservation of traffic, no exceptions. And zooming out a bit, we have Kirchhoff's voltage law, or KVL. This one states that the algebraic sum of voltages around any closed loop must be zero. Now think about this like taking a hike on a mountain trail. If a battery lifts you 10 feet up the mountain at the start, by the time you walk through all the resistors and obstacles and return to your exact starting point, you must have stepped down exactly 10 feet. The energy provided to the circuit perfectly, 100%, balances the energy consumed by the circuit. And what makes these laws so incredibly powerful is that they seamlessly scale up. We can take Ohm's law, KCL, and KVL and apply them to wildly complex multi-loop networks. By setting up just a few simple algebraic equations based on these loops and nodes, engineers can solve for every single branch current and voltage drop with absolute mathematical certainty. What looks like pure chaos to the untrained eye becomes totally predictable and completely solvable. So let's bring this all together. When we step back and look at the whole picture, electronics really isn't magic at all, is it? It's a wonderfully logical, deeply predictable system. Tiny, microscopic charges are forcefully pushed by voltage to create current. That current flows predictably through road maps built of active and passive elements. And every single tiny movement strictly obeys the unbreakable mathematical rules laid down by Ohm and Kirchhoff. Hopefully this explainer has given you a calm, solid foundation to visualize what's actually happening inside your devices right now. You really don't have to be a master mathematician to appreciate the pure beauty of this system. So I'll leave you with this. The very next time you plug in your phone or flip on a light switch in a dark room, take just 1 second. Ask yourself, can you picture that invisible highway of microscopic charges perfectly balancing energy at every single intersection? Thanks for exploring this with me today, and keep cultivating that curiosity.